The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to today's research results presentation on innovative evaluation of pre-stressed concrete box beam bridge designs. We have an excellent presentation panel for you today. So I'm going to cover a couple of quick housekeeping items, and then I'll be turning things over to the main PI. First, we will be accepting questions throughout the presentation. And I would ask that you please look for the questions box in the GoToWebinar panel, and feel free to drop me a hi or hello in there so you know that it's working. But that is where you'll be putting your questions throughout the presentation. We will not be unmuting folks just to keep the background noise down. So we request that you please put your questions in the question box, and we will stop partway through to address questions from our first presenter, and then again at the end to address questions that have come in after our second presenter. The other thing is we have been provided a copy of today's slides, and they are available for you in the handouts section of the GoToWebinar panel. If you have a problem downloading those, don't worry. They will be available later to you, as well as a final report and the tool that's going to be discussed on this research results presentation, all from the research website. And I'll provide you that information and a link in the chat in a little bit. So we are attempting to record this presentation. If we're successful, you'll receive a link to the recording. If we're not successful, it's a good thing you're here because you're getting the information live and in person, so to speak, over virtual connection. So with that, I'm going to go ahead and turn things over to Dr. Serhan Guner with the University of Toledo.
Thank you very much, Victoria, for the nice introduction. Hi, everyone. Good afternoon. Welcome to our final research result presentation. So today we are going to talk about a computer tool that we developed for innovative evaluation of prestressed concrete box beam bridge designs. I would like to start by acknowledging Ohio Department of Transportation for funding and supporting this project. Special thanks go to ODOT Technical Advisory Committee members Amjad Wahid, Grant Austin, as well as ODOT Program Administrator Vicky Faut. Finally, I would like to acknowledge Department of Civil and Environmental Engineering at the University of Toledo for providing facilities and support. Project team includes Yugesh, Maharjan, who did the main coding development of the computer tool, Suraj, Dhungel, who did assessment, validation, verification studies for this research, and myself, Serhan Guner, Associate Professor at the University of Toledo. Before we move on, I would like to thank students. ODOT STAR project is all about developing new talents, developing students. Yugesh and Suraj did a fantastic job. This is a master's study, but I think their level is much higher than a master's study. So I think they have proven themselves with this project. They are graduating in the summer. And if you are looking for a bridge engineer, so you can reach out to him, I think they would be a very good design analysis engineer. So we have 10 different headings for this presentation. We will start talking about what's road rating, what's prestressed box beam bridges, problem statement, project objective, how we develop EdBox, capabilities of EdBox, verification, user interface, and finally, we are going to have a live demonstration. For this, of course, we'll finish with conclusions at the end of the presentation. So now I'm going to turn it over to Suraj, who is going to talk about the first part of the presentation until slide number 26. At that time, we can take a couple of questions, and then we'll proceed with the second part, which is going to be more of a demonstration of the tool, capabilities, etc. Thanks very much.
Thank you, Dr. Guner. So we begin with the load rating. What is load rating? So load rating is the process of evaluation of a bridge's capacity to carry vehicular loads It is generally expressed in terms of rating factors or tons of vehicle weights. So there are some key factors for load rating. They are traffic patterns, vehicle types, bridge design parameters, and the structural conditions at site. So why load rating matters? Load rating is important to ensure the public safety, to help monitor the safety of structures over time. It also helps in maintaining planning and prioritization. It is required for posting weight limits and processing of the permits. So what are the methods for load rating? Generally, load rating has three main methods. The first one is load and resistance factor rating. This is the modern standard. Second one is allowable stress rating. This is the older method and is still used for the service limit state. And the last one is load factor rating. So let's introduce briefly about the pre-stressed box beam bridges. This is the simply supported bridges with precast pre-stressed box beam placed adjacent to each other. We can see the typical box beam bridge sections on the top right side of the screen. So almost 27% of the box beam of the bridges in the Ohio are box beam bridges. So according to Ohio Department of Transportation Bridge Design Manual, the design span of these bridges are ranges from 20 to 120 feet with a skew angle of up to 30 degrees. So these beam have single cell and multi-cell cross sections and are primarily used for short to medium spans due to their favorable span to depth ratio. So these bridges are also ideal choice where the clearance is limited. So all new sections from ODOT standards are single cell box beams, and some of the older sections from old ODOT standards are also multi-cell box beams. We can see on the bottom left side of the screen, there is a single cell box beam, and on the bottom right side, we can see the multi-cell box beam. So let's look into the problem statement. Load rating of the adjacent box beam bridges is labor intensive due to the large number of sections used, and it requires extensive calculations. So end calculations and general purpose load rating tools are complex and time consuming. Due to the lack of automated computer tools specialized for the load rating of these bridges, a reliable and user-friendly computer tool is needed. So to overcome these challenges, the project goal is to develop an innovative computer tool for the evaluation of precast pre-stressed adjacent box beam bridges. So to achieve this goal, we developed a computer tool named ADBox, which stands for Adjacent Box Beam Bridge Analysis and Rating. So you can see the logo of ADBox on the right top corner of the screen. So this tool is specialized for the load rating of precast pre-stressed adjacent box beam bridges. So we developed it using Visual Basic of applications and is included in a user-friendly MS Excel spreadsheet. So this tool is developed in MS Excel spreadsheet to reduce the cost and time required for learning sophisticated software. So ADBox is automated with approximately 3,000 lines of VBA coding. So this is the flowchart we adopted for the development of ADBox. So the orange chart in the flow represents the input parameters such as bridge information, material properties, box beam section properties, load rating settings. If the box beam section properties are from the Ohio standards PSBD 0207, we can directly use it from the drop-down menu in the ADBox. So if it is custom sections, we can give the manual dimensions like the older sections having multi-cell configurations. We can use it, we can input it, the dimension of those sections manually. So after inputting these parameters, ADBox calculations includes live load distribution factors, maximum movement and shear due to dead loads and live loads, movement and shear capacities of the beam, and finally the calculation of load rating factors. So for the custom sections, it can also calculate the section properties automatically. So after calculating these calculations automatically, ADBox displays the final load rating factor results as a rating factor value, which are grouped based on the load cases. So let's look into the capabilities of ADBox. So AdBox can handle rigorous calculations automatically. The calculations include dead loads and live load distribution factors, so calculation of bending moment and shear forces, calculation of nominal moment and shear capacities, and finally the calculation of final load rating factor values. The dead loads include the input from the bridge information. Live load includes the 15 vehicle types required by Ohio Department of Transportation Bridge Design Manual. So these vehicle types include design vehicle, Ohio legal vehicles, permit vehicles, emergency vehicles, specialized hauling vehicles, and ASTO legal vehicles. So AdBox has also capability to load rate custom vehicles with up to 35 axles. The moment distribution and shear distribution factors are calculated based on the distribution factor method. So during the calculation of the distribution factor, we need to compute the torsional constant. So for the single cell box beam, torsional constant is calculated using Saint-Venant equation, whereas for the multi-cell box beam, we applied the shear flow framework for torsional analysis. So the detailed process of these calculations can be viewed on the project report. So AdBox calculate bending moments at the exact location of the maximum moment rather than at the 1/10 of the span method. So we can see on the figure, so when we move the design truck HL93 along the span of the beam, red circle indicates the exact maximum moment location, and black circle represents the center. So we can see that the exact maximum moment location has the maximum moment value compared to at the center, which indicates that the exact maximum moment location method calculates more accurate value than 1/10 of the span method. So AdBox is developed to calculate the maximum moment at the exact location of maximum moment. So typical shear check point is located at a distance equal to effective shear depth, that is dB away from the face of the bearing of the support. We can see that on the figure on the left, the distance dB away from the support. So additional shear check is also performed where the shear reinforcement and spacing changes. So we can see the additional shear check locations on the bottom left figure. So this is the point where typical shear check location is performed, and this is the point in the beginning of region 2 where the additional shear check location is done. So AdBox is developed to calculate shear force at both typical and additional shear check location. So AdBox calculate nominal moment capacity using the rectangular stress block method, whereas it calculates the shear capacity using the modified compression field theory. So the detailed procedure of these methods are found on the project report section 3.1.3.5. So finally, AdBox calculates the final load rating factors using limit state for 3 distinct procedures. So the procedures are design load rating, legal load rating, and permit load rating. So legal load rating is performed using strength 1 limit state, and additional check is done for inventory loading using service 3 limit state. And legal load rating is performed using strength 1 limit state. And finally, permit load rating is performed using strength 2 limit state, and optional load rating is also done using service 1 limit state for permit vehicles. So these load rating are performed using load and resistance factor rating method for strength limit state, and allowable stress rating methods for service limit state. So the verification of the AdBox is another main task. So verification of AdBox include 2 distinct methods. One is verification with independent hand calculation. So to check the accuracy of AdBox, rating factor values from the AdBox are verified against the rating factor values from the independent hand calculations. So another is comparison with the ASTO BRR. So to check the reliability of AdBox, we compared the value from the AdBox with the value from the ASTO BRR. So let's look into the verification with independent hand calculations. Verification independent hand calculations are performed for 18 sample bridges with 15 vehicle types. So rating factors from AdBox are compared with the results from independent hand calculations. So calculated RF values from the independent hand calculations matches well with the RF values from the ad box. So we found pretty good results. We found the mean of approximately 1 and coefficient of variation of almost 0%. So this is the sample verification table for the design vehicle HL93 inventory. So we can see that the ratio of rating factors of ad box to independent hand calculations have mean 1 and coefficient of variation of almost 0% for both non-skewed and skewed bridges, including single cell and multi-cell configurations. So this proves that the rating factors from ad box matches well with the independent hand calculations. So this is the verifications for the remaining vehicle types. We can see the chart on the left. Ad box rating factors is on the horizontal axis, and ratio of rating factors of ad box to independent hand calculations on the vertical axis. So we can see the red line as the mean line, and each point represent every vehicle types, that 15 vehicle types specified in ODOT-BDM. So for each vehicle types, the ratio of rating factors of ad box to independent hand calculations perfectly align with the mean line. So this indicates that the values calculated by ad box is aligning with the values from the independent hand calculations. So we can see the table on the right side of the screen. So this is the coefficient of variation of ad box to independent hand calculation values. So we can see that for every vehicle, the coefficient of variation is almost 0%. So therefore, we can say that the mean of approximately 1 with a CB of nearly 0% confirms the accuracy of ad box. Now let's look into the comparison with ASTO-aware BRR. So rating factor values from the ASTO-aware BRR are compared with the rating factor values from the ad box. So comparison is done for 18 sample types for sample bridges for 15 vehicle types, and including the 4 custom vehicles. So rating factors from ad box matches well with the BRR. We found the pretty good result over here as well. We found the mean of approximately 1 with a coefficient of variations of up to 3.72%. So this is the sample comparison table for the design vehicle HL93 inventory loading. So we can see that the ratio of ad box to ASTO-aware BRR has the mean of 1 and coefficient of variations of up to 3.72%. So for both non-skewed bridge and skewed bridges, including single cell and multi-cell configurations, so we can say that the rating factor values from ad box matches well with the BRR. So this is the similar chart we have seen in the comparison with independent hand calculations. So the left chart shows the comparison of ad box to BRR with all the vehicle types, including the custom vehicle. So we can see the rating factor values, rating factor ratios of ad box to BRR are aligning with the mean line here as well. So this indicates that the values calculated by ad box align with the values from the ASTO-aware BRR. So on the right side, we can see the coefficient of variations of ad box to BRR. So this shows that the coefficient of variance of up to 3.72%. So nonetheless, any deviations for anything that is less than 5% is generally acceptable. So we conclude that a mean of approximately 1 with a coefficient of variations of up to 3.72% confirms the reliability of ad box.
Perfect. Thanks very much, Suraj, for the nice presentation. So now we are going to move on to the second part of the presentation.
We do have a few questions in the question box.
Yeah.
If you're ready for that.
Mm-hmm.
Okay. The first one wants to know, is this program for only non-composite bridges? Are you able to use ad box with composite box beams?
Composite box beams are what is currently being used in Ohio, elsewhere. So that's the main intention. So you should be able to use it for composite, but also you might be load rating an old bridge with non-composite deck. So it allows for both composite as well as non-composite.
And the next question is, have you identified the reasons for the somewhat larger differences between AdBox and BRR when compared to AdBox and hand calculations?
Suraj, if you want to go back to the previous slide, I think it was slide number 25. First of all, the discrepancy, if you compare two different computer programs, there is always going to be some discrepancies, right? Anything less than 5% is a very acceptable discrepancy. So 3.72, which is the worst case scenario, considering all 18 bridges are well within the margins of error, right? There are a couple of reasons for this one. One reason is AdBox is calculating the moments at exact locations, which are a little bit higher than what BRR calculates. So it is actually more accurate than BRR. So a part of the discrepancy might indicate that AdBox is more accurate. It doesn't mean the opposite. So that's one reason. The other reason is the moment capacity calculation. This one, we are using rectangular stress blocks. BRR using strain compatibility. So definitely there is going to be a couple of percent discrepancy there. So these are the two main reasons for discrepancies, but there could be some other minor reasons depending on the algorithms programs. But nonetheless, we consider anything less than 5% is a good result.
We have one more question, and then we'll move on to the second half of the presentation. Does AdBox utilize the severe corrosive condition that ODOT requires be assumed?
So I'll direct that question to Yugesh. There are some options in the program. So Yugesh, do you have any answer to this question?
Yes. So AdBox uses both conditions required by Ohio BDM. So it can also load rate based on severe conditions at service limit states.
Mm-hmm.
Yeah.
Perfect.
Okay, you guys should just need you to accept the presenter status that should have popped up on your screen. If it did it not pop up? Oh, there you go. Good.
So now we see, yeah. All right, so Yugesh, you can get started with the second part, demonstration as well as capabilities of AdBox.
Yeah, thank you, Dr. Guner. Okay. So to provide a simple and user-friendly interface, AdBox is developed with two primary tabs, which are visible at all times. They are main tab and calculation summary tab. It also contains on-demand tabs, which are only visible upon the user request. And it has an optional tab to present the moment and share envelopes due to the selected vehicle type on any simply supported bridge. So this is what the primary tab of the AdBox looks like. And it has simple and user-friendly interface with well-organized input and output. So it also contains drop-down menus to reduce the input errors and has buttons to use the default values. The load rating is computed by a single click of the button, which says compute load rating, and it displays the load rating factors properly grouped in as per the vehicle type. So this is what the calculation summary of AdBox look like, and it presents summary of all detailed calculations involved. It also contains buttons to display and hide on-demand tabs, so the detailed calculations can be viewed utilizing these buttons. So this is the on-demand tab, particularly for the capacity calculations. So this is displayed when a user wants it to display it, and user hides it, it will be disappeared. This is the optional tab of the AdBox for the moment and share envelopes. So it generates the moment and share envelopes in both tabular and chart format, and these calculated values do not contain any distribution or impact factors, so appropriate factors should be applied. The generated value can be copied and can be used for independent analysis. So now I'll give a live demonstration of the AdBox. So the main objective of this demonstration is to demonstrate the application and key features of AdBox, we'll be using version 2.6. The key highlights of the demonstration will be a brief overview of user interface of AdBox, a live walkthrough of the capabilities and features. I'll be doing an example load rating of a sample bridge located in Ohio and which is provided by ODOT. So I'll go through input and output, the main tab, a calculation summary, on-demand tabs, input of custom beam sections and custom vehicles, and I'll also go through the optional tab. So after opening the AdBox, we can see that there is a About tab which contains the general information of AdBox and the standard it uses. So the primary tabs are in green color, which are main tab and calculation summary tab. So the primary tabs, main tab is where the user will spend most of their time and perform the load rating. The primary tab contains 4 sections. Section 1 is for the bridge information. Section 2 is for material properties. Section 3 is for box beam section properties. Section 4 is for load rating. You can see that the input and output cells are color coded. So the orange cell are for the essential input. The orange cell with asterisk in the description are built-in input and they can be changed. The gray cells are for optional input and the white cells are for the output. To start the load rating, we can clear the data already present in the AdBox by clicking the Reset All Data button. This will clear all the data present in the AdBox. We can start by inputting the name of the bridge and construction year. There is also option to input the name of the person who is performing the load rating and date for documentation. So I'll be using the information sample bridge with these information for the load rating. So it will be a 66.5 feet span bridge with width of 32 and skew angle of 12 and information as shown. And the section of the box beam I'll be using is presented at the right side of the window. You can see the traverse section and the framing plan at the right side of the window, and I'll be using the details provided in these drawings. So we need the total span and width of the bridge, the single lane width, which is 11 for this case, the in offset, the width of the bearing will be 6 inch for this case, bearing type is steel tube railing, which is shown in the traverse section of the drawing. So the width of the barrier is 0 for this case because it doesn't occupy any space of the beam bridge width. The design span and roadway width are calculated as per the details provided. Then we need to provide the type of the beam section. We can select either non-composite or composite type box beam. So for this case, the type of the beam is non-composite. So I'll select non-composite from the drop-down menu, and the thickness of the deck slab will be 0 for this case. So as we input the values, we can see that there are nodes that will help user to what value they need to input in the input cells. We can see in the framing plan that it is a non-skew, it is a skewed type of bridge. So we need to select skew from the drop-down menu, and the skew angle is 12 for this case. The surfacing material is asphalt surface with a thickness of 8.67. Then we need to input the diaphragm details of the bridge. We can see in the framing plan that there are 6 diaphragms. So let's input value 6 for number of diaphragms. So after inputting the number of diaphragms, the input regions for 6 diaphragms will be displayed in the add box. So we can input the position and thickness of diaphragm in add box. I have noted these values from the drawings and I'll be using these values. After that, we need to input the bridge appraisal rating. It is basically from 0 to 9. So let's input 9 for this case, and the condition factor for this bridge will be automatically calculated. To include the miscellaneous loads, we can also input the additional beam weight or additional barrier weight. So let's input 0 for this case. After filling the bridge information, we need to fill out the material properties. So AdBox contains built-in input for these material properties. So I'll be using the same values for this case. I'll only change the area of strand, which is 0.167 inch square. So we can select the type of the strand from the drop-down menu, which can be load relaxation, stress relief, plain pre-stress, or deformed pre-stress bars. Then we need to input the unit weight of the surfacing material. So for asphalt surface, it is 0.145. And for the barrier, it is 0.080 for steel tube railing. After inputting the material properties, we need to input the box beam section properties used in this bridge. We can select the type of the box beam used from the drop-down menu. So this drop-down menu contains all the sections listed in ordered standard PSBD 0 to 07. So these cells, all the beams included in this drop-down menu are single cell box beam. I'll come to the multi-cell box beam section later in this live demonstration. For this bridge, the beam section used is B2148. So let's select that beam. Then the section geometry and section property for the beam will be automatically extracted from the standard table. After inputting the beam type, we need to input the number of pre-stressing strand provided in the beam. So we can see in the section of the beam, there are all total 30 strands in 2 layers. So let's select 2 for layer of strands provided. The first layer contains 18 number of strands at 2 inch from extreme tensile face, which is at the bottom flange. 12 number of strands at 4 inch from the tensile face at the bottom flange. We can also input the strands at the top flange, but these values will not be used for calculations. We can also input the debonded strands. For this bridge, there are 2 numbers of debonded strands positioned at 2 inch from the tensile face, which is also at the bottom flange of the beam. After that, we need to input the longitudinal reinforcement bar if present in the beam. So for this case there is 5 number, two longitudinal bars at the bottom flange. So let's select number 5 bars, 2 numbers at 2 inch from the extreme tensile face. After inputting the pre-stressing strands and longitudinal rebar details, we need to input the shear reinforcement details. As mentioned previously, we can calculate the shear reinforcement, the shear rating factor at region 1 and region 2 as specified. So for region 1, we will be using the shear spacing and details at as mentioned as A in the part elevation and B for region 2 in the part elevation. After inputting these shear reinforcement details and all the details required, we can then move to the section 4, that is load rating. So in this section, we can define the settings for load rating and get the output values for the load rating. We can either select the exterior or interior beam for load rating. Let's select the exterior beam for now, and the riding surface condition as smooth surface. So after that, we need to input the dynamic allowance for each vehicle types. So we can use the buttons provided to use default dynamic load allowance. We can also manually input the values, specifically for the permit and custom vehicles. For vehicles moving in crawling speed that is less than 10 miles per hour, we can input the value 0% for dynamic load allowance. After that, we need to input the values to calculate the service limit states. So we can use the default input for the service limit state. So we can select the pre-stressing strand condition to low to moderate or severe corrosion from the drop-down menu. Let's use the severe corrosion condition. After that, we need to input the average daily traffic in one direction for legal load factor. So let's input 8,000 for this breeze. So after inputting that value, the live load factor for that legal vehicles will be calculated. The live load factors for emergency vehicles are based on the FAST Act, and I'll leave that value for now. After that, we need to input the permit load condition. These are based on the ASTO MBE. So let's use the routine or annual type of permit vehicle. So these drop-down menus are dynamic and will be changing based on the permit type selected. The live load factors for the permit vehicles will be calculated based on the load condition selected. We can also input the custom vehicle by selecting yes from drop-down menu. I'll be coming back to that later. After inputting all the details and information required, we can move to the load rating results section and compute the load rating by clicking the compute load rating button. So we can see that there is a note saying click on the compute load rating button and some input values have been changed. So whenever any input is changed, this note will be displayed, helping the user that they need to compute the load rating again. So let's compute the load rating. So after the load rating is computed, the load rating factors will be displayed grouped by the vehicle types, and it also contains the checklist to display the checks performed by AdBox. So you can see that the inventory rating factor and operating rating factor for design load vehicles as well. So this inventory rating factor is computed based on the severe corrosion condition of the pre-stressing strand. So we can also compute for low to moderate corrosion condition for the pre-stressing strand. So after computing the load rating, we can view the calculation summary results in the calculation summary tab. So this is the calculation summary tab. So it contains all the details of the summary of the calculation involved in the load rating. So it contains the on-factor moment and shear calculations due to dead load and live load. It contains the summary of capacity calculation and the summary of the load rating calculated both for interior and exterior beams. We can display the detailed calculation by clicking the show buttons. So let's display the moment and shear calculation calculated by AdBox by clicking this button. So after clicking that button, the detailed calculation for each vehicle types will be displayed. So you can see that there are multiple tabs for each vehicle types. So this method is applied to give a clean interface in AdBox. We can hide them by clicking the hide buttons to keep the AdBox clean. You can see that there are also buttons for distribution factors. Moment and share envelopes are varying across the bridge. So these values do not contain any distribution or impact factor, so appropriate factors should be applied. You can also see the exact maximum moment along the bridge, which is displayed with the red dot. Let's go back to the main tab and see how we can input the multi-cell beams by selecting the custom from the box beam section used. So after selecting custom, we need to input the width of the beam and height of the beam and some section, the section geometry of the beam. So we can select number of waves to 3 and input the value of the middle wave for the multi-cell box beam. We need to input the area, moment of inertia, and the distance from central to extreme bottom fiber for that custom beam. Let's select B2148 for now. We can also add a custom vehicle with up to 35 axles by selecting yes from add custom vehicle menu. So after selecting add custom vehicle, we can input the number of axles of that custom vehicle. I will be using 19 axle custom vehicle for this demonstration. So after inputting the number of axles, input cells for the configuration will be displayed. At the right side of the window, I have noted the configuration of the 19 axle custom vehicle. I'll be using this value for the demonstration. After inputting the vehicle configuration, we need to select the custom vehicle load condition, which is similar to the permit vehicle. I'll be using the special or limited crossing condition for this vehicle. So the live load factor for this custom vehicle will be calculated based on ASTA MBE. Then we can compute the load rating by clicking the compute load rating button. We can see that the load rating factor for the custom vehicle is also calculated. Now let's see how AdBox handle erode and invalid inputs. For a box beam bridge, the typical total span is from 20 to 120 feet. So let's say a user input invalid input, let's say 130 feet for the total span. So the AdBox will warn user that invalid input has been inputted in this cell. So and the input cell will be highlighted in red text. Let's say the user misses this error and computes the load rating. So while computing the load rating with invalid input, AdBox will display an error message to warn the user they have inputted the wrong or invalid input and they need to correct it. So the program will terminate the calculations until the values are corrected. So let's use the correct value. So then the text will go back to normal. We can recompute the load rating by clicking the compute load rating button. So the load rating is successfully calculated and the load rating factors are displayed in the load rating results section. As we can see that AdBox can be used to load rate the precast prestressed box beam bridges in less than 30 minutes. I'll go back to the presentation and ask Dr. Guner to present the conclusion of this research.
Thank you very much, Yugesh, for the nice demonstration. I would like to finish this presentation with a couple of conclusions. The first one is AdBox. That's what we developed. This is the first dedicated tool for the load rating of prestressed adjacent box beam bridges. It has a simple and user-friendly interface. There are some error and warning messages implemented to reduce the possibility of input errors. You can complete load rating in less than 30 minutes for 15 vehicle types as required by ODOT redesign manual. You can load rate a custom vehicle up to 35 axles. If you are analyzing or load rating another bridge, not adjacent box beam bridges, you can still use AdBox to generate moment and shear envelopes, and you can use it in another software for any other type of bridge. So it's a general capability. And we also aim to facilitate learning the overall process. We are giving additional information, commentary. There are some text which comes up as you enter your input to facilitate learning the load rating process. So that's pretty much it. I would like to thank you very much for your attention. I would like to thank both students very much for their tremendous efforts. This wasn't something that has been done in a couple of months. They made tremendous effort with this one. So we would be happy to answer any questions about the first part, about the second part of the presentation.
Great. We do have some additional questions for you. And this one I'm going to read you came in right after the second part started, so it may be related to the first part. It says, what about shear check ODOT requires for box beams?
Shear check is done according to what ODOT BDM requires. We developed this tool for ODOT, so definitely we are following their requirements. We are also going one step further to do additional checks at every shear reinforcement change location. But maybe students, you can, Suraj, Yugesh, you can turn on your webcams, come to the discussion. Let's make this open discussion. You can unmute yourself and you can give your thoughts about the shear check according to ODOT BDM. If there is anything. Yeah, so I think that answers the question. This is the slide for the shear check based on HTO, LRFD.
Great. The next question, how did you add in any degradation factors such as spalling and or exposed strands?
That would go to Yugesh.
Hello, am I audible?
Yeah, we can hear you.
Okay. You can see my screen, right?
Yeah.
Okay. So we need to input the bridge appraisal rating for that conditions. So this is from the report generated by inspection of the bridge. So the bridge appraisal rating is ranging from 0 to 9. That is coming from the site investigation and from the report. So it will contain the condition of those beam, the strands, and everything. So the condition factor will be generated based on that appraisal rating. I hope that answers that question.
Yeah, so you need to input the condition based on inspection report and the program, and then you'll see the factor. It could be, less than 1, so you will see what factor the program is using for the deteriorated condition.
Yes.
Great. The next one says that they have 2 questions. I'm going to read it all through, but if you need me to go back, I'll be happy to read a section again. It says, why was the program developed? To have something specific to Ohio, or does this do something other commercial programs do not? Does the program check the longitudinal steel as part of the shear check? Is the method described in the report?
I'll answer the first part, why we developed this one. Right now, you don't have very many options. Your pretty much only option would be BRR. If you have a adjacent box beam bridge. An H2BRR is a general purpose tool. You need to really customize it to your specific box beam section details. It's not for ODOT, it's for the entire nation. So there is a tremendous effort involved to customize BRR to load rate your specific bridge. On top of that, you are going to be getting tons of output because BRR is not just for simply supported beams, but it's for continuous beams. Your box beam is pretty much simply supported in many cases. Because you are using BRR, you're going to be hit with pages of output, and it would be very difficult to analyze, understand. So, if we did that study, if you take a box beam bridge and if you analyze it with EdBox as well as BRR, you will see that you are going to be making tremendous effort, order of magnitude more effort to analyze it with. BRR, you need to learn it, you need to understand, you need to get the license, which is expensive, right? What we developed can be used for counties, little offices, 1 engineer, 2 engineer, very low learning curve, it's free. So that's the motivation of what we developed in this study. So I think that's the first question. The second one, any one of you, Yugesh or Suraj, would you like to answer the second question? If you remember, if not, we can ask Victoria to repeat the second question.
Repeat it. Does the program check the longitudinal steel as part of the shear check? Is the method described in the report?
Yeah, definitely. I mean, if you are using modified compression field theory, you need to calculate at epsilon x, and epsilon x calculation will, in the denominator, you need to consider the longitudinal reinforcement and its conditions. So it's part of the procedure. It needs to be considered if you are doing it according to modified compression field theory. Yeah.
Yes, Dr. Guner, that is correct.
Great. Next question. Which version of LRFD specifications were used in developing this program?
We always use the latest version, but I'll let students to give specific information about the version that they used.
Yes, we use the LRFD 2020 version for this development.
Next question. Why was rectangular stress distribution chosen versus other methods?
There is always consideration of complexity when we develop tools. Strain compatibility approach is used by H2BRR. It is more accurate and it can handle general cases. You might have a tapered section, you might have unusual geometries, and strain compatibility method would be more accurate in that case. So the question is it needed for adjacent box beams? The answer is no in many cases because we have rectangular sections. We decided that it's going to really complicate things a lot, will not give sufficient benefit because you have the neutral axis. Either you are in the deck or you are going into the web. So you have only two cases, and in both cases, you are dealing with a rectangular section. So I think rectangular section is a good simplification. So that's why we choose that approach.
Okay, a question that is a follow-up clarification from an earlier question. Longitudinal steel did not mean epsilon x, meant 5.7.3.6.3, where you check the embedment of the longitudinal steel due to additional tension due to shear.
Mm-hmm. Yeah, I'll let students talk about it, but I'm familiar with the modified compression field theory. So you're talking about, at this support location, your bar should have enough remaining capacity to balance the additional stress coming from the shear check, because shear is diagonal and there is going to be a horizontal component that's going to be taken by the longitudinal reinforcement. So that should be done, but I'll let the students talk about how they incorporated that into EdBox. Or if you have to look at the specific code clauses, we'll take a look and we'll can we reply to the question?
Sure, we can have you draft a response and we'll send it out to that individual.
Yeah, because we need to look at the clause, and sure, students really followed every single clause which is in the code, so they should have an answer, but they may not remember exactly the clause number right now. That's a good question. Thank you.
Great. Last question. Is a trial version of AdBox available? If so, where can we get it?
We are finishing the project. It's going to be the full version, actually. We did a lot of iterations, a lot of testing, debugging. So the project will be ended at the beginning of June. So EdBox, the final version, version 2.6, should be available through ODOT research website. We are also going to be recording, sharing YouTube videos, other documents as well. I have a university website and I'm going to create a page, and it's also going to be downloadable from that page. So it's a free tool and you would have multiple options to download, test it, use it, starting next month or in 1.5 months in June.
Great. Thank you all for your time today. It's never easy to present on a technical topic, let alone virtually. So we sincerely appreciate you doing it in this manner so we can get the information out to as many individuals as possible. With that, we're going to wrap things up. If you do have any further questions, please feel free to reach out to the research section. I have put a message in the chat box with their website address, where the report and the tool will be available soon. We appreciate everyone's time, and to our students, we wish you the very best of luck in the future. And with that, we're going to go ahead and wrap things up. Have a great afternoon. Take care, everyone.
Thanks very much. I appreciate it.
Thanks.
Thank you.